of inertia of a disk. In that, suppose we consider first about an axis passing through the center of the disk and perpendicular to its plane. Moment of inertia of a disk about an axis passing through the center of the disk and perpendicular to its plane. Now, suppose you consider this is the disk. Suppose this is the disk which rotates about a transverse axis. Transverse axis means a axis which is perpendicular to its plane and passing through the center. Suppose we consider capital M is equal to mass of disk is equal to, I write here, pi r square rho. If r is the radius and rho is the density of material, then mass can be written like this, pi r square rho. Capital R, radius of disk. O, suppose this O is center. Suppose rho, mass per unit area. See here, not density. This is areal density. We call it as a mass per unit area. Now, suppose you consider this disk is divided into number of concentric. See here, concentric means having same center. Number of concentric rings, and all these rings contributes to the surface area of the disk. Suppose this is one ring having radius small r. See here, small r is the radius of one ring, and this capital R is the radius of total disk. Then suppose small r is the radius of the ring, and suppose I consider here, suppose this dr, this much. Dr is thickness of the disk. I write here, suppose small r, radius of small ring, and dr, thickness of small ring. Now we consider here moment of inertia of this small ring. Suppose I consider here di is moment of inertia of a small ring, then it can be written like this, that is m r square mr square, where small m is mass of ring and small r is radius of ring. Suppose this is equation number 1. Then this m can be calculated like this. Suppose you consider small r is the radius of ring, then I will write here 2 pi r, this is the circumference of ring, into dr, this is the area of ring, into rho, this is the areal density, which is equal to m. That means m is equal to, I will write here small m means mass of the imagined ring, then m is equal to, I will write 2 pi r dr into rho. And if we put this value, suppose this equation number 2, if we put the value of mass of ring from equation 2 in equation 1, then we get here di is, I will write here, that is 2 pi r dr into rho, this is mass, into r square, and therefore di is equal to, I will write here 2 pi r cube rho dr. Suppose this is equation number 3. Now total moment of inertia of the disk can be calculated like this. I is equal to integration of di, and I will write here, suppose equation number 4, we put value of di from equation 3 in equation 4, then we get I is equal to 2 pi r cube rho dr, and here r comes, then we write the limits of r as 0 to capital R. That means value of r varies from 0 to capital R. Therefore, I will write these limits of integration. Now I will take constant quantities common outside the integration, 2 pi rho integration 0 to capital R, r cube into dr, and therefore I is equal to, I will write 2 pi rho as it is, and we solve the integration like this. Integration r cube dr means I will write r raised to 4 upon 4, and limits are here 0 to r, means 2 pi rho as it is, and if we put the upper limit, I will write r raised to 4 upon 4, and lower limit is 0, minus 0 means same thing, and I will get here this 2 cancels with this 2, means pi rho r raised to 4 upon 2. Now suppose equation number, I think 5, then therefore I is equal to, suppose I will write like this, pi r square rho on one side, pi r square area of the disk, and we multiply area by rho, then this is the mass of the disk, then pi r square rho on one bracket, in one bracket I will write r square upon 2, and therefore I is equal to mr square upon 2. This is the equation number 6. This is the moment of inertia of a disk about an axis passing through the center of the disk and perpendicular to its plane. Now here I will get radius of gyration k is equal to root I upon m, then k is equal to, this m gets cancelled, and we get k is equal to square root of r square upon 2, and k is equal to r upon root 2. This equation number 7 gives the radius of gyration of the disk in this case. That means whenever axis are passing through the center of the disk and perpendicular to its plane, this is the radius of gyration. Now suppose we consider extension of this. We consider, suppose, second thing here in the same article. I will show, that is secondly, we will only change the position of axis of rotation. I will write about an axis coinciding with any diameter, about an axis coinciding with any diameter. That means we consider, suppose I will draw a small figure here. Suppose this is the disk, and axis of rotation we consider any diameter. Suppose this is the diameter, suppose x-axis as a diameter, and about this axis the disk rotates. Suppose I consider this is the y-axis of our coordinate system, and we consider z-axis like this. Okay, perpendicular means this one, see here, perpendicular plane of figure, this is the z. Now suppose Ix is the moment of inertia about x-axis, Iy is the moment of inertia about y-axis, and Iz, I can't draw here, Iz is the moment of inertia about this axis. Then according to principle of perpendicular axis, I can write here Iz is equal to Ix plus Iy, and this Iz we have known. That means mr square upon 2 is equal to Ix plus Iy is same. Disk either rotates with this axis or y-axis, then moment of inertia is same. I will write 2Ix, means Ix is equal to Iy, therefore I will write 2Ix, and therefore Ix is equal to mr square upon 4, and same is the Iy. Iy is equal to also mr square upon 4, or about any diameter. Suppose you consider this one, this diameter, any diameter, number of diameters are there. See here, number of diameters we can draw. Then about all diameters, this moment of inertia is same, mr square upon 4. And if we calculate k here, then k is equal to root I upon m k is equal to, m gets cancelled, and square root of r square upon 4 is r upon 2. This is the moment of inertia about any diameter. Now another extension here about an axis coinciding with tangent. Means we can say, suppose I will draw a small figure, try to understand. This is the small blackboard. Suppose this is the center and this is our x-axis in this diagram. Now suppose this is the tangent T. Then about this axis you know the moment of inertia. What is the moment of inertia? mr square upon 4. Now this distance is r. Then according to our principle of parallaxis, IC is equal to IO plus mh square. IC means moment of inertia about center of mass. IO, suppose this point is O, then IO, I will write here. Then IO plus mh square. Then I will convert this, that is IT. Sorry. IO is equal to IC plus mh square. IO means this point O, IC means this point C. Then IT is equal to, I write here, IT is equal to mr square upon 4 plus m, and this distance h means r. Therefore I will write mr square. Means here I can write mr square upon 4 plus mr square. I will write 5 by 4 mr square. This is the moment of inertia about tangent. Now here in this case the radius of gyration is root 5 upon 2. This m get cancelled because root I upon m is there. Root 5 upon 2 into r. This is the radius of gyration, and this is all about the moment of inertia of a disk about all these three axes. Thank you.